Welcome all, and thank you for attending this session. In case you don't know me, I'm Jeremy Turner. I'm DOT&E's Chief Scientist. I'm thrilled that we have Paul Wach here, who's a professor at Virginia Tech National Security Institute, to tell us about how digital engineering impacts test and evaluation. All right, over to you, Paul. Thank you.
Yeah, thank you. So I've got a bit of an intro slide for me. And so I teach digital engineering at Virginia Tech, and it's pretty interesting. We try to incorporate a lot of these concepts into how we teach. In fact, I've got one of our Ph.D. students here, Brant Sandman, and he's going to give a poster this afternoon. So if you have like extra hard questions, you should definitely save them for Brant. Just to give you a little bit more background on me, I like to say, who is Paul? I'm not really a snooty professor, so you can call me Paul. But if you really want to, I tell my students you can call me Professor Paul. Or if you need to understand how to pronounce my last name, you just say like Doc Wach. That's how you pronounce my last name. And a little bit about myself. I got a BS in Biomedical Engineering. Supposed to be one from yeah, okay, there we go. I got a BS from in biomedical engineering from Georgia Tech, and kind of had a really roundabout trip of getting back into the defense and national security enterprise and industry. Focused a lot of my research on the kidney, and I was really on this mission to develop an artificial kidney. And then because I was the only American in my research group, I was voluntold to go work for one of the national labs. And ever since then, I've been in this like energy, national security, defense industry. That led me to eventually getting my PhD in systems engineering because I really wanted to like tame the chaos of the defense industry. And in this case, it was really more in the Department of Energy realm, or if you're familiar, the National Nuclear Security Administration. So I cut my teeth really in the nuclear security, nuclear weapons industry and enterprise. And it's pretty interesting, like how they do things. They, in fact, have been doing a lot of digital means for a long time since they don't really test. Like they have to rely on a lot of simulations and validating those models. So that's come into play for where and how I've shaped my career and life since then. Did work for the Aerospace Corporation. I still do some part-time work for them, and I was a digital transformation lead for them on their corporate board. About 2 years ago, Virginia Tech offered me this job to come into academia, and I've really appreciated it. It's given me some flexibility to maybe take what I've learned in industry and help shape how we can do business a little bit free of maybe some of the day-to-day firefighting. And so that's some of what you're going to see here. And, just to give you, this is not like a single project we work on. Actually, Jeremy's really been our sponsor. And we have a cross collaboration mostly on this particular part of the project. Laura Freeman, if you know her, since we're at IDA, you probably do. But she's the PI on this, and this is a project that's been going on, and we've been slowly kind of folding in how do you transform test and evaluation to like be fitting for the digital paradigm. We have at least these are actually not even our full team, but these are probably some of the main contributors that really would, I'd say, would jump out and say like, yeah, they're doing work. Obviously, you got Brant Sandman, our PhD student here, and Jeff Kerr, if you've worked with Virginia Tech a bit on any of these projects, you might have met him. Former Lockheed Martin guy, Tim Sherburne. He's more of our modeling lead. And then we have University of Arizona. It's been really nice to work with them. You can recognize one of them, Dr. Alejandro Salado. He will keep his hair like that and be dressed like that no matter who he's meeting with, even if he had to meet with like an admiral or general. So he's very confident in himself. He's a very knowledgeable guy. Same with Joe Gregory. He's from the UK. And he's our ontology expert. So if you've heard the word ontology, which you probably have at this point, he's been really ingrained and helpful in terms of shaping a lot of the work that we do. I do want to give you a background too, like where I come from. So I work for the National Security Institute at Virginia Tech. And a lot of what we do is really one, like translating a lot of the academic research to more practical application. For me, it's very important to bring what I learn in academia back to practice, back to industry, and help make us more efficient and more effective. And so I really like that part. Also, like working with students. That's another part that we do is really shaping that workforce. So like Brant, I really enjoy teaching Brant and helping him to learn some of that industry and why what we do is important, and really tying it back to that mission. Just a little bit of background to further on the National Security Institute. We have 3 divisions within our institute. One's the Spectrum Dominance Division. That's really where the electronic warfare and electrical engineers mostly sit. And we have the Mission Systems Group. That's where most of the platform folks sit. They more or less are the aerospace and oceanography type engineers. And they do some other things like obviously autonomous vehicles. And I work with them on probably a little bit of everything. We have a couple of them that are actually on this project as well. I'm just going to say it's probably the best of the divisions, the intelligent system divisions. Which happens to be where I work, but that's where a lot of the AI is located. And so pretty much everyone in that division has some shape or form AI expertise. Individually, I do a lot of work on generative AI and particularly the whole craziness with the large language models and small language models and et cetera, et cetera. And it's been pretty interesting. We have a broad spectrum. It's also where our expertise for digital engineering and systems engineering sits. So that's partially where I was brought on board to start bringing in that systems and digital engineering perspective. All right. So I'm going to kind of start shifting maybe a little bit into, now that we got that, I want to actually get a little familiarity with the audience. It's because I can take this and present it from my perspective, but I really want to shape it to your perspective. So if you're comfortable, I'd like you to give like a quick intro, what your job is and years of experience and interest in the topic. So I'm going to start with Jeremy.
Okay, so again, Jeremy Werner, I'm DOT chief scientist. I have a fairly broad portfolio, part of which includes digital transformation, which this sort of digital engineering work falls into. In terms of background, Ph.D. in experimental particle physics from Princeton, and that was in 2011. So that kind of tells you my years of experience.
Yep. Brant?
Brant Sandman, I'm a first year PhD student at Virginia Tech, working in the industrial and systems engineering program. I also work under Paul at the National Security Institute. So this is basically directly my work and not all my work. Trying to clarify. But I also am taking courses on this and I have a big interest in shaping my career throughout grad school. So
You want to say? All right.
My name is Lorenzo Neal. I'm a newly recent IAA hire, and recently I've been working on systems evaluations for different systems within the Defense Department. And so one of the tasks I've been assigned with is doing test evaluations for certain systems, and so that's why I joined this tutorial, just to get a better sense of test evaluation concepts.
Okay, nice.
Hi, I'm Perry Ann Herring, Dr. Herring. I spent most of my career at academia teaching math, but came back, well, right out of college. My after I got my master's degree, I worked for the Air Force for a short period of time. Went into teaching for a number of years, and then in 2016 came back to work for the Department of Defense. I work for the 413th Test Squadron out at Duke Field, and you've heard of Duke, but you've probably heard of Eglin. And Duke is probably about a 20-minute drive from Eglin. And we're the only Air Force developmental testing squadron. And so we test all things rotary wing. And we have a sister squadron that is really looking into this type of innovation. And so we are looking just to add tools to our data team.
Okay, thank you.
Hi, I'm Melissa Stanley. I work for IDA. I've been here for 3 years doing test and evaluation, so I'm really looking to learn more about how the digital engineering impacts it.
Okay, good.
Hi, I'm Michelle White. I also work for IDA. I actually got my Ph.D. in 2022 from Virginia Tech. So nice to see a lot of the room. So right after that, I got my degree in biomedical engineering, but then kind of switched to for 2 years. I was working for a contracting company supporting the Navy, looking at modeling and simulation test beds. So I took more of just the system engineering role as well as data analyst. But now that kind of brought me here, so I support DOT on this whole program that stands.
Brittany Williams. I've been at IDA for 11 months now, fresh out of grad school. Got my doctorate in chemistry from Northwestern with the focus on drug formulation. So I did a complete pivot because now I support DOT&E with missile systems for air defense. And I'm just interested in figuring out how digital engineering will impact a lot of the test and evaluation that we do, because we rely on modeling and simulation a lot.
Yeah, and I imagine drug discovery, there's a lot of statistics
Yes.
within drug discovery, so that's actually not too much of a leap. Okay, yeah.
So Bill Bryant, more commonly known by data in this space. I'm a technical fellow with NTSI, support DOT&E, come out of an operational background, one of the random fighter pilots who they were talking about downstairs. Did that for about 25 years, and I've been doing cyber things for 8 years. Made pivot from the academic road. Most of my research is focused on risk assessment in cyber physical systems, various quantitative methods. Been doing a fair amount of MBSE, ID, modeling, simulation, all related to that.
Good, thanks.
Brittany Fisher, I work at the Stats UE. I've been there for just over 2 years now. With that, I have 5 years of experience in the industry. A lot of my experience has been in design experiments. So digital engineering is certainly a new topic.
Okay, good.
Good morning. I'm Marty Marshall. I'm also with the Stats COE. About 5 years. The acquisition for nearly 40 years. Currently supporting the Sentinel program at the Air Force Base.
Nice, okay. All right, let's we had more people join online. So I'm gonna go down the list online if you don't mind introducing yourself. So we got Allie.
I know people can't use the microphone. They're
Oh,
not down and they can't talk.
shoot, okay. Well,
I will say that I was in this room yesterday for a workshop, and that was initially an issue, and the IT person had to come turn something on.
oh, it's not a huge deal then. I've got let's see, yep, somebody said looks like our mics are disabled. Okay.
Yeah.
All right. Well, we'll make do. Hopefully that was a pretty good representation of what the room and what the makeup of the classroom is. So all right. So it looks like we got a pretty broad spectrum, some obviously some statistics, data analysis, and fighter pilot, right? We got some various parts of the spectrum, fairly new, right? Fairly seasoned, and yeah, and government contractor, I'm assuming, right? So that's pretty good makeup, and means I'll be fairly flexible in how I present this. Okay. So I know sometimes I like to start with this like whole why change thing. Has anybody ever read like Edward Deming book? Oh man. Okay. So his quote is like it's not necessary to change. And why? Because survival is not mandatory. And that's kind of the truth. You know, I've heard other expressions from my past, like better is the enemy of good enough. But what happens when you're not good enough? You need to do better. That's kind of where we continue to be. So with digital transformation and examples being digital engineering and model-based systems engineering, those are really part of the technology. And so we're kind of continuing to see within DoD these like realized risks, like the F-35. And you know, I use this one. I was from Augustine, and if you've ever read this book, Augustine's Law, it's kind of interesting. If you can't see this quote in the back, I'll read it real quick. But it says, in the year 2054, the entire defense budget will purchase just one aircraft. This aircraft will have to be shared by the Air Force and Navy 3.5 days each per week, except for leap year, when it will be made available to the Marines for the extra day. And so that's just kind of indicative of some of the things that we're trying to fix with digital engineering and digital transformation. Is that generally familiar? Are you experiencing this? I know I've lived where we're still generally kind of in this stack of like papers and trying to shift to something that's more along the lines of data centric. So mostly what we're trying to do too is, or in the case of this presentation, is really focus on verification and test and evaluation. Where if you don't live in this, which I know most people here do, the V&V verification is like, did we build it right? Like, so did we build it according to the specification? And validation is more of, did we build the right thing? Now, test and evaluation, I thought I took that out, but it's something that's really more on the government side, and where you have like developmental operational tests. And I'm sure many of you, having lived this, can talk to the specifics of T&E even more than I can. So I won't dwell on that too much. But why we're focusing on this and why it's important from a digital transformation perspective is I'm going to use this, which Ken Seneschal sent me earlier this week. He actually guest lectured at my class and kind of collapsing a lot of the V, which is more enabling earlier verification, validation, and test and evaluation. So that's really what we're trying to accomplish. All right. Here's also the vision piece too. So phase 0, this is where unfortunately we are the majority of today. In fact, I have to tell my students that we're still using things like fax machines frequently. And they're like, wait, what's a fax machine? And oh, by the way, like what's a pager? And you know, I spent some time at the beginning of the semester showing them how we might do things today a bit slower with the document process, where some things may literally be written down on a napkin or said in, you know, conversation, and, you know, hopefully documented somewhere, maybe on someone's computer but it's probably siloed and you can't actually access the data. So due to issues like that, we're kind of becoming more model-based, and you'll probably recognize the tool here, but it's Cameo Systems Modeler, and be familiar with the systems modeling language. So that's where we are today, which is kind of beginning that conversion, but it's not quite there yet. We still have quite a bit to go, and some of the things that I've lived from my experience is the kind of focus more on the models and the diagrams rather than the data. And like for example, within SysML and Cameo, there's like 20 something views that you can use. Gosh, with and you add on the unified architecture framework, and like there's like, what are there? Like 200 different elements, and off the top of my head, maybe like 90 something different views that you can create. And so a lot of times we're focusing more on the actual like images rather than the data itself. And some of the complexities that we're actually living from experience are when you have to have like the actual dynamics between different tool platforms, and ultimately really getting to that dynamic data set so that you can really leverage past information to influence your plans and execution going forward. And that's where we are. Like that's what most of this presentation is about, is getting to dynamic data sets. So if you're a statistician and you're familiar with Bayesian networks, this is kind of what we're trying to get to. But the idea of how you aggregate that confidence in the system so that you ultimately have confidence in the fielded product. And I've got a little bit more information on that, and we're going to go into that in more detail. But it's not just like how you aggregate the confidence, it's also how you include things like the schedule elements. And again, how you might change your plans going forward based on the current state of information. There is a phase that we're calling the maybe it's the final phase. It's at least the phase that we've defined for a future state, which is this phase 3. And what we're going for there is really a mathematically underpinned models and data. And that now allows you to really have interoperability, reuse, leverage some more advanced data analytics with the artificial intelligence, machine learning, things like knowing the fidelity of your data throughout the life cycle. So like data lifecycle management. And that's really when we're going to get to have this like library that also interplays with your phase 2 and your confidence in systems a little bit different than we can today. Any questions so far? Nope. All right. So using proxies to prove in the methods and tools. So this part, I want you to first like imagine that within engineering any system, with acquiring any system, we're basically going to use a proxy. We're going to use some type of surrogate. And why would we do that? Well, it's kind of difficult to use like real systems and programs. It might take 10 years to actually acquire a system, so we're not going to take a 10-year mark. There are classification concerns, and the systems that I lived on, the nuclear security industry, they're like 30-year lifespans, maybe 40, in some cases kind of like 60 years. And so you can't really like wait for a program. And so in time, we really looking for how that like adapts, and we want to have like a concise set. And so we can really overcome the things like the F-35 and the James Webb telescope, where it was almost canceled. Just kind of reiterating this of the use of proxies. So we use a lot of different things throughout our engineering of systems, modeling simulation, breadboards, prototypes, like testing aerodynamics on a reduced scale and wind tunnels, like the test range. Those are really just surrogates for the actual operational environment. I mean, even if you have a live fire test, it's really a surrogate or proxy for the actual real environment that a warfighter and is going to see. So, I mean, some of those that I've used in the past are kind of looking at the progression of things from a breadboard to like a more of a prototype, maybe defining the form a little bit more. And as you progress through, and then eventually it looks like something completely different from what it started. Like it's completely unrecognizable from that breadboard to like the actual end product. Now, what this has to do with the presentation is that we've decided to go a route that goes away from real programming. And what we want to do is to be able to have something that we can control from birth to retirement. And we started off searching for like what an appropriate surrogate or proxy would be. And you know, if you think about the types of things that we wanted to incorporate in this to really prove in the process and methods, like we need something that we can really control. We need something that has a physical counterpart and has a digital counterpart. Because you know, digital transformation generally relies on something real. Yeah, I mean, you can look at from a software component side, but there's really a cyber, physical, and even like intelligence aspect to this. So we want something that has all these different facets. We include like the mission lifecycle, the system lifecycle, the acquisition lifecycle, the data lifecycle, and maybe even be able to mold these into different like story arcs that are more indicative and more realistic to what's like faced within the acquisition of a real system. So there are a couple of systems out there that we kind of explored. We'd start off, I mean, one of the ones we really explored was this Skyzer. So has anyone in the audience heard of Skyzer? Yeah, we had at least one. No? Minimal? Wow. Okay.
Now you gotta tell us what.
Yeah. Okay, so Skyzer was a quasi fictitious system in itself, where it was created by NavAir. It was, but a lot of the work was done at the Systems Engineering Research Center. And what they did, the kind of the bummer sticker, I don't know if you can see it with, I wonder if I can move this, but it says at the bottom there that it's doing everything in models to demonstrate art of the possible. So they had, if you know, I kind of expected that most people would have some awareness of this, but if not, let's see. So it was based on this image that you see over here, which is the Bell Eagle Eye search and rescue vehicle. So it has kind of to the left, you can see where it's search and rescue at sea, and it has various sea states. Really essentially of the weather conditions, the like size of waves that it has to perform in. And they created several like models, a whole ecosystem around, or I should say digital ecosystem around this whole idea of the Bell Eagle 11. They took existing information out there, unclassified, and just worked it into several models. At the time, this was referred to as model-centric engineering. So this is more, it's closer to the lines of what I would call like the phase 2 piece of the digital test and evaluation. They, if you're familiar with Cameo and SysML, there were like 20 something models in here, which was something that when I first was exposed to it was a little bit of a surprise. But part of the piece of that getting to digital T&E even is that there's not necessarily like one model to rule them all. essentially you're going to have various sets of like data and models that have to be harmonized to really create this like effective and efficient transformation, which is really about communication and decisions. So that took me back a little bit. There are other pieces too, is that there's also not one tool to rule them all. There, in this case, yeah, there are 20 something models within Cameo Systems Modeler, but there are other tools that they also use, like for schedule. For example, they might have used like MS Project for, let's see, for a lot of the multi-physics type optimization. I think they used, I can't remember the tool they used, but an example would be like ANSYS Systems Toolkit, where they could do a lot of this analysis. In this case here, they had the tested airworthiness. So part of this is actually a pretty compelling story for why digital engineering is appropriate for test and evaluation. This does present a pretty good art of the possible. And so what they did is they had conflicting requirements. One was for the cost. And so they had different designs for the landing gear. So going back to the C states, they had like the top C state. I don't remember actually which one it was, but it's basically the most C state 5. Okay, so it was the most arduous. So we have two people familiar with it. So going back to C state 5. Oh, okay. So they had, which is the most arduous weather conditions. So essentially, the idea would be that this search and rescue UAV would have to land at a high rate and high speed, which essentially causes a lot of challenges on the landing gear. And they had two different landing gears. One was hydraulic, and one was let's see, electric. Yeah, hydraulic and electric. And when I start doing the analysis, it turns out one of the two, I believe the hydraulic one, was a little bit more expensive. So it didn't meet like the cost requirement. But then you have the hydraulic one, which was less expensive, but couldn't quite meet the same landing rate. So there was the like landing rate was 180 knots, but the hydraulic one could land at 170 knots. And so what that enabled them after that analysis was to kind of feedback into the ecosystem and say, hey, we can't actually meet this requirement. We need to present this to a decision maker who can say, you tell us what to do. Do you want this landing rate and this landing gear, or do you want this other landing rate with this less expensive landing gear? And how this actually worked was there are several models. Like you essentially had a surrogate for what would be like a joint environment for like the government and contractor, where they could start looking at more of the abstract models in Cameo and looking at more of the architectural elements. What's the composition? What kind of tests would you actually run? And in the model in Cameo, they ran a lot of the cost analysis too. So you can do some parametrics within Cameo Systems Modeler. But it's not necessarily, and you shouldn't be using it for like this more computationally intensive type design and analysis. So that's where you need some external tool that's not your MBSE tool, that's not Cameo Systems Modeler. So what we did is to provide some like bounding parameters to the different designs, which were then conducted. The analysis was then conducted in this external tool, which then they could feedback, yes, we can either meet this 180 knots or we can meet the 170 knots. And so that type of feedback ultimately to like the decision maker is really what we're trying to get through. And so to do that, you need different tools, you need the models and data to be harmonized across different tools and potentially even different ecosystems. All right, I'm gonna pause there. Any questions, thoughts? I thought I saw like one or two questions online. Yes.
What do you think about using Cameo as to create a meta model so that all the other models connect to it? You know, overall, how the system interacts perspective?
Yeah, so that's actually how the Skyzer set of models did this. There are some caveats there. And the caveat there is that what's happening in practice that I'm consistently seeing is that you essentially create what's called a profile or a meta model within Cameo, but that doesn't necessarily ensure like the data is consistent across like an ecosystem. And so that's where we throw in the word like ontology or the O word and start defining your ontologies, which is really the approach we've been taking. And I think a lot of the industry is taking as well. So make sure that you're actually harmonizing the data and the models across the ecosystem of tools. Does that address your question?
Quick question. And if you're going to get to this down the road, that's fine. But we've made a lot of promises in digital engineering. They're all the same promises we've been making every 10 years or so using some new methodology back to run stuff. Or actually further back than that. So my question is if we're not seeing the results that you're talking about. So the ET7 is just as over budget and just as late as any other airplane we've ever done. So can you address a little bit of why we're not getting the benefits that we were hoping to get at this point?
Yeah, I can share. And so I got to preface that this is Paul Wach's perspective. But I mean, it does hold a fair amount of warrant. And looking across, I partially point to the Sentinel program. You know, I believe that there were some challenges with the Sentinel program. I'm aware of that.
Well, the Sentinel program's in the middle of a gigantic non-McCurdy breach. So I mean, we can use that as an example.
Well, yeah, but so I don't remember. It was whoever was was it Kindle that said that we're still experiencing like 20% efficiencies. So it's not that it's not helping. What I'd say is that I think this is kind of proving that we need some of the test beds that we're creating to really prove in some of that value. Because I see exactly where you're going from. With all the research even done at the CERC, they talk about there's one going back a couple years that says like what are the benefits? And turned out that this survey across everyone that's used MBSE, there was a lot of hype. And it's really and somewhat can be viewed as maybe somewhat of a placebo. But that doesn't mean there's not necessarily like value to it. I mean, some of it, I'd say we haven't quite done digital engineering. The more I survey across the whole defense national security enterprise, I haven't seen anybody really holistically get there. And so some of what we're going to see is we probably need to invest in further test beds. And as the tools and everything mature, that's when we'll really start realizing the value. And it's also difficult to measure something that doesn't happen. Yeah, Jeremy.
I chime in with
go ahead.
my perspective. So, I mean, the way I see this is that MBSE digital engineering is still a very nascent technology. And what in a way, what we're trying to do now with complex hierarchical systems data, right, which is at least 4-dimensional, 3 dimensions in space, 1 dimension in time, at least, right, is akin to what happened with relatively basic 2-dimensional business data sets, right, in the first quarter of this century. So what I mean by that is we sort of saw like the emergence of data science, the emergence of a lot of ways of handling business data and making it very efficient. right? And now we're kind of trying to do that same thing, but with much, much, much more complex data. And if you look at the way that that worked for business data, right, it was all about building software as a service at an enterprise scale on top of primarily open source technologies. I look at like where we are with MBSE and we don't, it's still very much a desktop type exercise. There's some, I'll call them like centers of excellence or counter examples where there are proprietary enterprise tools. But until you can interact with a SysML model through an open API, just like you can a SQL database, through any myriad number of tools, we're not where we need to be. So I don't think that we're not there in terms of enterprise tools right now.
Yep.
I would also say I think the whole cost savings thing is a little bit of a red herring. I'm not saying that MBSE won't meet the cost reductions. Alternatively, what I'm saying is cost reductions is not the primary reason why businesses adopt new technology. They adopt them to survive, right? That's why everyone's building out these huge, data centers using NVIDIA GPUs and LLMs, et cetera. It's not because they want to, it's because they have to.
Any other questions?
But I agree, there's a lot of hate.
I think that's what Jeremy was saying was kind of like a great internal kind of what I was thinking too, because coming from, I can only speak for the Navy, pushing. But I know when, in my experience trying to adopt MBSE or trying to use Cameo, a lot of it is, well, we have the tools that we know. I think people get very much like, this is what, I don't know how to use this, or like, I tried to use it, it wasn't very user friendly, so I'm gonna go back to what I know. And I think going back to there's like not a lot of open sources too, because I can think of Cameo, I think they exist to like enable lit, but there's not really a lot of backing for the community. Hey, this isn't, in my experience, this didn't work for me, or like, can I see kind of what your profile looks like, what your kind of diagrams, and I didn't know if you had any suggestions of how we can kind of push past that barrier of it. Yes, we know there's like this cost constraint, but there's also resources that allow you to use this on like, a network or something. But how we can do more data sharing, or do you all have any type of like ways that you're kind of data sharing, or obviously too, there are 10Ks that are part of that, or like classified data with this ways that maybe people can see more, this is what this diagram looks like, this is how we're able to get to what you need to get to in terms of meeting this requirement or making a diagram to show what these requirements are.
Yeah, I mean, so I have to, again, caveat that some of this is Paul Wach's opinion. And I think it's really, the more we focus on creating meta models or profiles in Cameo, that makes us more focused on the tool itself rather than on the data and the models. And so you have other MBSE tools like InnoSlate, for example, which is grounded in an ontology inherently. And so you can actually share that data. There are open APIs. So some of the things that I'm working on in other research is how do we convert SysML v1 to v2? And I'm focusing on how do you do that within Cameo, because that's where a lot of my sponsors are using. And then there are various ways you export that data. You've got your XMI data, and then it's really specific to the tool Cameo, like how that data is structured even within XMI. And so it's creates some complexities with, and I should say complicatedness maybe, and how you extract the meaning of those data and models and maybe use them in different tools. So the way that we are approaching it on this project, and that is more, again, I'm going to use the O word again, ontology, but it's not just about the ontology too. It's also about creating a platform that leverages that ontology to help harmonize the data across different tools. So if you're creating something on ontology and you're mapping it to some other ontology, then that helps you to map the data and make it consistent across even different programs, projects, etc. And I'm going to talk about that.
Thank you.
Yeah, you're welcome. Any other questions before we move on? Okay, so what I've tried to go through up to this point is that we have proxies. Like the whole idea of Skyzer was that we wanted to find something to really prove in the art of the possible. But within this project, and we've kind of focused on creating a proxy and something that we can really control and grow and use for this test bed, which, we're using to prove out right now, or how do you do digital test and evaluation. But, there's a caveat too, even within that, like we want to make it as realistic as possible, but also something that we can make sure that is of a low enough complexity level that we can intuitively wrap our brains around it. So we have this mission that we call Operation Safe Passage. And, you can imagine that essentially what you have to do is some troops have to move through a particular area or supplies or something along those lines. And you have some command and control, maybe some UAVs, some satellites, something that really can detect, in this case, like some threats, maybe like some landmines or something like that. And, based on identifying those landmines, you can then task some like UGV to go like clear the path or to go confirm that this path is in fact safe. And then you have that backwards loop of communication saying, yes, it's safe. So that's kind of more realistic of what it happens in practice. So I should actually title this a little bit different, but we've been working on this and kind of transforming into that case study that we can control, which I should call Operation Safe Lego in some ways. I think it was either Jeremy or Laura that came up with the toy. Yeah, tots.
Wasn't me.
Toys off the shelf. So we've decided to latch on to Legos. If you're familiar with the whole idea of like the EV3 Lego robots, or now more recently the Spike Lego robots, like that's what we're working on. So here's an example. There's the real UGV on your left, and then this is actually the EV3, the old Lego robot on the right. So what's neat about this is that there are multiple configurations that you can use. There are some common elements across the systems. And like you can do, like there are different tire sizes that you can use. There are some different motors that you can use. There are a lot of different parts that you can use. And then there's this common computer computational and communication device that's in this case referred to as the brick. And what that enables you to do is to have alternate configurations for like different terrain, for example. I mean, maybe in one case you want to use track, maybe in another case you want to use tires. Let's see. So, but within the idea of having that computer brick and that commonality, it allows you to incorporate things that we're not quite incorporating yet, but in the future, like product line engineering. And it also enables us from a digital engineering perspective is to test all these parts in a full rigor that we might want to test something in practice. So if we wanted to test each of these structural elements, let me see if I can, like from a stress strain mechanical perspective, like we can do that, and it's low expense. And if we break this, that's okay. And also there are other things that we can incorporate too, like supply chain analysis. So I mentioned that there are two different versions of the robot. There's the EV3, which we show here, the EV3 Mindstorm, and there's Spike. So if you look at it from the EV3 robot as being a legacy system, you can kind of incorporate the idea of like supply chain analysis and logistics of having to do with a finite supply. And so that maybe gets you to some interesting decisions like, hey, do we buy these parts from this unknown vendor, or do we want to make these online? And then we can, to what level do we need to test the parts that we've procured versus something we make in-house to ensure like the assurance, I should say. Yeah, to have high assurance of the reliability of the parts. And even from there is a cyber physical aspect to this. So there's the computer brick. So what we're incorporating are things like there's a software configuration, and there's the hardware configuration pairing. It has multiple sensors. So in this case, like what you see here, so this is like a proximity sensor, and here you have a color sensor. And so that enables you to do things like detection, and I should say, again, a proxy for detection. And going back to kind of the realistic idea versus the proxy. So realistically, it's, a UGV could be like multi-theater, multi-domain, multi-terrain, multi-environment, could be in the desert, could be the mountains, could be in a jungle, could be on a beach. And so what we've tried to do is to start having like a proxy for this that, again, we can control. So in our case, we have the University of Arizona, which is more of a desert climate. And then we have Virginia Tech, which is in Southwest Virginia. So we're testing these robots within those, quasi-extreme environments. And so that allows us to get various performance measures across different terrains and different environments. So we've developed a few KPPs for this. I don't have the numbers on here, unfortunately, and I don't remember them off the top of my head, so please don't quiz me. That might be a question for Brant later in his poster.
Sorry, we've got a couple of questions.
Okay.
Is the physical model of these things considered digital engineering?
Okay, that's actually a really interesting question. How do I answer that? I'd say there's a component of digital engineering in the fact that you look at some of the buzzwords associated with digital engineering is that there's a physical pairing with a digital aspect. And so that allows us to do things like model validation. So in this case, let's just say we were testing the physical, like a physical piece of the structural, of one of the structural pieces. Let me go back. Okay, so let's just say we were doing like a stress chain testing of all of, these various connectors. Can you see that? Oh wait, I'm over here. Yeah. So let's just say there is a physical counterpart to this. So the digital piece comes in that we can do a lot of the physical testing. And if we continue to make things the same way, then maybe we can reduce our physical testing. So it's really, the way I would phrase it is it's a pairing with the physical counterpart. Do you want to add anything?
No, that sounds good. So another question, which we have some answers to, so I'll try to describe both the question and the answers. What's the name of the Lego kit, and are they available for consumers? And then the answer was first Lego League competition is where these are used, and that, yes, we think they're available for purchase.
Yeah, so the one that's shown right here is the EV3 Mindstorm. They're no longer made new, which adds to some of the fun of what we're doing, but you can procure them on eBay. In fact, that's where we got ours on. We just bought a couple from eBay. And they unfortunately ended it, I think, roughly during the like COVID timeframe, maybe 22, and then started making the Spike robot. The Spike robots you can buy from the Lego store. So we bought our Spike kits from Lego, and they come in usually like a base set that has the computer module, some motor sensors, some various wheels, maybe tread, and yeah, so you can have different configurations. Plus, you can buy the expansion pack to where you can, yeah, expand to like more complex designs. Was that all the questions?
Yep. Thank you.
All right, KVPs. So we have the several KVPs that we've focused on, and things like your detection rate and your classification rate, and yeah, even things like, yeah, safety, adaptability, false alarm rate. So of these, I'd say are some of the ones that we focused on more recently would be on the detection rate and more of the false alarm rate for the detection and classification. Yeah, yeah. One of the ones I don't necessarily see here that's maybe not a KPP is that we have focused on would be the more along the lines of the duration and terrain that you can take these vehicles through. Yeah, let's see, pathway creation, time taken to clear a path. So it would somewhat tie back to like the pathway creation time, but it's more of a derived set of tests that we would need to conduct. And so I think that maybe on the, yeah, let me skip that for a second. Okay, some of the realistic threats. So we've talked a little bit about the realistic threat being like a landmine. And why you would want a test bed? Well, I mean, yeah, I had one sponsor say, what's it going to cost to develop some of these things? And they say, well, in this case, we're saving lives and a lot of hardware. And by using this test bed to do this. And so our proxy, we've actually used sticky notes for our proxy, and it's produced some really interesting results in terms of the classification and the different sensors between the legacy EV3 Mindstorm and the Spike kit, which I'll go into in a bit. You know, our first thought was, well, how are we going to do a proxy? And we're like, yeah, let's just put out some sticky notes and, you know, see if it can detect these. Turns out it kind of mislabels some of those, which I wouldn't have entirely expected. A lot of what it seems like they use some of the sensors for are more of the idea of like tracking a line so it can go in a particular path. And so some of the like more industrial robots, they put like, you'll see like lines on industrial floors where the robots just like are looking downward and they see that line, and that's kind of the path that they know they have to follow. And so I think because of maybe that and maybe the quality of this particular color sensor, it's maybe not able to detect some of the sticky notes. We talked a little bit more about also just adding perturbations to some of the sticky notes, like drawing figures on there. So you've seen with maybe AI a few years back, where you take a stop sign and like, you know, draw one mark on it, and suddenly the AI can't detect a stop sign. And it turns out we don't actually quite need to do that, but we will get to some of that, adding some of the text, some of those perturbations to really see and push the limits of this. And let's see, so our DoD, or sorry, our getting to some of what we're trying to do, which you really need an environment, a digital engineering ecosystem or environment, depending on what you want to call it, to really have to really conduct this digital engineering and to really harmonize that data. And realistically, within DoD, as Jeremy pointed out, we're not quite there yet. And within our set, we have a proxy environment also. And it's really a subset. This is actually a simplified view of what we have. And I'll go into detail on these throughout the rest of the presentation. I think that's a good moment for a quick pause and see if there are any questions. Okay. All right. Kind of going back to the research team and who we have. So obviously Jeremy Warner is on the sponsor side for us. We do a little bit of work with APL and GTRI on some of this. They're doing a little bit of related work. On the Eric side, I don't think I actually said this earlier, but this is sponsored through the Acquisition Innovation Research Center, which is a sister organization of the Systems Engineering Research Center that's focused more on acquisition. And what the ERIC is, it's pronounced ERIC. It's a UARC, a University Affiliated Research Center that has several different universities in this. Like, let's see, examples, obviously Virginia Tech and Arizona. So we're two of the organizations or two of the universities that are part of ERIC and the CERC. And we have a fairly large research team. You know, some of the names that I didn't show earlier, Kelly Esser, she's helping to do things like the IDSK, if you've heard that term, it's the Integrated Decision Support Key. So how do you really take a lot of the data from test and evaluation and put it in a format that the decision makers can understand, and also like what data is important as well. We have John Gilbert, who's another person that I didn't talk about earlier. He's in the Mission Systems group at Virginia Tech, National Security Institute. And so he's helping us really shape a lot of that analysis and some of the multi-physics modeling that we're doing on these Lego robots. And then again, we have our University of Arizona friends, Alejandro and Joe.
We do have a couple of questions. I think one of them refers to a prior slide. Are threshold and objective values parallel to realistic system metric set for the KPPs? Key performance parameters.
I think so. I don't have that open in front of me.
Yeah, that sounds right. Okay, and then from Scott Hunter, I can definitely see why the digital engineering and digital modeling is helpful. One advantage was production could take many years. Building an accurate digital model seems like it could take just as long. What are your thoughts on that?
Right. Okay, so if I understood the question, it was focused on two parts, the fact that it existing takes a long time, and two, that creating a model could take a long time.
Right.
Right? Oh, yeah, okay. Oh, that's a really good question. Okay, let me think about that. Yeah, okay. All right. So one, I'd say that the models only need to be as good as they need to be. And I think maybe a risk in some ways of doing digital engineering is not modeling for the sake of modeling. And I've seen in practice a fair amount of people like focus on, say, creating every view of the unified architecture framework rather than saying, here's the subset of data that we actually need. And oh, by the way, here's a way of presenting that data in the context of specific stakeholders. So I think it gets back to like a value judgment, and some of it, what we're going to see are, you know, what's the abstraction and elaboration of some of the models. You know, going back to my background on finite element analysis and computational physics, fluid dynamics, like it's kind of the same thing where eventually you get to the point where there's so much fidelity within the model or so much detail that it really produces no new value, but it takes infinitely more time. And so I think that's something that we have to figure out is what's that level of detail that's really appropriate. And I think some of what we're also going to see is that as we mature the methods and tools, that we can really enable the reuse so that maybe that idea of creating models is reduced in at least maybe time and increased in effectiveness. So some of what I'm working on right now outside of this project is how do we use generative AI to do some of this. So I've got a fair amount of looking at how do we use the systems modeling language version 2, which has a textual basis in conjunction with language models. And so we're doing a fair amount of how do you actually take input from subject matter experts and automatically generate a lot of these models. And it turns out it can do this fairly well. It doesn't mean you don't eliminate the human in the loop. It just means that you have a means of maybe achieving some efficiencies that may otherwise be the case or otherwise not be the case. Maybe reduces some of the needs for expertise on detailed knowledge of some of the modeling because we're using it from one, how do you take subject matter expertise and convert it to a lot of these models like SysML-v2, and how do you take the SysML-v2 models and convert that back to a format that a subject matter expert can actually interpret. And so as we, one, develop some of the models to feed into the basis, as you know, a term that's used throughout industry is usually like reference architecture. You could say reference models, reference data sets, et cetera. But that helps us at least have a starting point for comparison that we can achieve some of these efficiencies when you combine them with more of the, let's say, cutting edge technologies like generative AI. So it was a fairly winded response, but I think I addressed the question. Any follow-on questions?
Got an idea to throw out there for well, people have a job. The person job description is this is a model. And they might then phone the fact we're talking about modeling. But if your job is motivated on an outcome that's useful to others in a different way, maybe it's a different way to find the end of the path that could result in something useful. Digging deeper into the system element, making models. Modeling is complicated, right? You have to invest a lot of time and effort in learning the tool, feature rich, become good at it. When do you stop? Is a big question.
So, I mean, I have some perspective I could add. I'm not sure if it answers the mail exactly, right? But one way of looking at XML models is they're like a design tool, okay? They're similar to a blueprint or like CAD computer-aided design, kind of the next generation of that. That's how I view them, right? And they're the next generation of computer-aided design because they can build in some dynamics in terms of how system requirements, right? And specified behaviors sort of flow across and progress through the system, right? Having said that, they're just blueprints. They don't tell you where to put the nails or where to put the adhesives, et cetera, et cetera. It's not the instruction set to actually build the thing. So it has utility in terms of design, traceability, requirements, et cetera, but they're descriptive by sort of tactical in the sense that it's not the actual code that makes the system do what it does in the real world. Now you can contrast that to what is happening in the semiconductor industry, where they have supercomputers, hardware stacks, software stacks to very, very highly accurately emulate chip behavior using actual design, the actual design instructions, right? Including firmware and software that they can run on these supercomputers before they ever actually manufacture the chips to more or less ensure that the chips are going to behave as expected when they actually are manufactured. So they call that hardware accurate digital twin. There's some other terminology that they use, but I think that's pretty interesting and kind of like the gold standard for where hopefully we can eventually get. Again, difference being in the semiconductor industry, you actually emulate and get out the design instruction or the manufacturing instructions.
So basically making sure like actually get software.
Yeah. 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 And of course, this works at the scale of a chip, right? Or maybe a very small subcomponent, right? A motherboard, something like that. What we're trying to do with a full DoD system like an F-35 is, insanely.
Yeah, I think I'd add that to address the question, we'd have to include some trades for data governance, meaning like what's the data lifecycle? What data do we actually need? Do we have the capacity to store the data? And ultimately, to support the communication and decisions that we're hoping to make more efficient and more effective. And Jeremy, I saw one question about a white paper, something, is that?
Right, so that's kind of a sidebar or a side thread that's been going on in the chat about model-based test and evaluation master plan development, or otherwise sort of intelligent test and evaluation master plan development. So I'll address it.
Okay. Any other questions? Nope. Okay, these are some of what we've been working on. I know Jeremy just mentioned this, the MB-Temp, or model-based test and evaluation master plan. Some people are referring it to as a digital temp. That's one of the big pieces that we've been working on. And another one is the IDSK, the Integrated Decision Support Key. So that's the one I mentioned. I'm not really prepared to talk to that one today. So if you have questions, we'll have to hold those for another time. But there is some work going on, and essentially, so what the IDSK is, it's I think so it's been defined what that integrated decision support key is. So it's a lot of the content that you need to support decisions for test and evaluation, and the form that can take. And I will definitely defer to Jeremy on this, but it seems to be able to take a fair amount of different forms. So some of what's being worked on, or maybe what's the most efficient or most effective way. Recall Jeremy working on some SQL databases that take the structure of the IDSK and allow it to present. I think at GTRI and APL, I think they're doing something that's more along the lines with how do we use Cameo to present that information. And the way I believe our team is working on it at ERIC is more that we're looking at it from a perspective, it's about the data and independent of some of the tools. And so we can present that in various tools like Confluence, or I think we're using our Shiny, which is basically just an app for creating a dashboard. MBRA is the model-based risk assessment. So that's one that I'm not prepared to speak on today, but that's some work being done at APL and also at Virginia Tech. It's essentially how do you include a lot of the risk assessment within the test and evaluation, and what at least the approach that is being taken on the ERIC side is trying to look at more of how do we incorporate things like STPA, the systems theoretic process analysis. How do we include things like systems and cyber resilience engineering in the process of developing your risk assessment? And how do we make sure we have end-to-end mathematical underpinning in the risk assessment that's maybe more agnostic of some of the tools?
That's one of the projects I'm on. It's actually mission-based risk assessment. Not specific model.
Got it.
Using model.
Okay. I will change that. Yeah, and last is this Operation Safe Passage, and we're calling it a simulation, so it's more of a simulation in the sense that it's not necessarily digital, but has like a simulation of the acquisition process where there's a digital and physical counterpart. So here's some of what we've done on the model-based temp. So I've used the word ontology a bit. As I said, Joe Gregory in Arizona, they've been a lot of pivotal in developing a lot of these ontologies. And so they're been continuing to develop that. I'll go into it in a little bit more detail on some of the next slides. We're developing some common like reference architectures, meaning like more or less exemplars of how we populate the ontology. That's a lot of the work that we've done. And let's see, we've integrated that with a lot of the policy out there, like the DoD 5000.89, DoD 5000.97, I believe as well. And starting to incorporate things, as policies change and new methods and tools come up, we're incorporating that within our set. Any questions? Nope. Okay, here's a view of some of the model-based temp. And I've got more slides to kind of go on this. But in this case, I'm going to use I think I'm going to actually walk over here. So in this case, what you have is the DoD instruction 5000.89. And what you see here is the visualization of an ontology that is created on the basis of DoD 5000.89. So this allows us to incorporate that commonality that's independent of a particular tool. So can't remember your name, but I know you asked a question kind of along those lines about the meta models and then the data sharing. Yeah. So this is kind of getting toward that. I'll keep expanding on this. This is one of the pieces that I'm going to keep expanding on. So you can see things like here's the lead test organization, and let's see. Yeah, chief development tester defines a particular role. And you can see that there's an activity here for develop the temp. And here's another one for develop the IDSK. And the person responsible for that is the program manager. And you can see how things like the IDSK and the actual temp are something that are dependent on each other. So in this case, I think if I'm reading this right, it's basically saying that the temp contains the IDSK. Interesting. And yeah, let me see. So I've got more detail on this, so I don't want to give too much away yet. But essentially what you're going to have is you're going to have a multi-tool ecosystem. It's not going to be just one tool. What you want to do is have some way of like integrating the data that's both the ontology as well as maybe a tool. I'm going to go into this tool we've been using Violet for our purposes. You can see over here we have Cameo Systems Modeler, but oh, by the way, we also have SysML-v2, which we're using in a Jupyter Notebook. And we have other things like Jama and Jira for some of our schedule LMS as well. And how this works is based on all this data, you can actually publish a view, which would be the temp. And yeah, I'm going to go a little bit more into that one in the future. Questions on this yet? Okay, I'm going to go back to this, but I want to show you that this is some of what's what eventually you have a bunch of data. So on the previous slide, what I showed you is that there's a bunch of data, a bunch of models, different software platforms, and all this ultimately has to be viewed for a decision maker. It can come in different forms, but what we're showing here is one version of a dashboard, where in this case you don't want to see, how many tests have you conducted, how many things are upcoming, and if they're successful or not. When they are on the schedule, their approximate duration, and oh, by the way, like some definition of whether they've been successful or not. So this is an example of how a temp and the information that goes in the temp could be visualized within a dashboard. And here's some of what we've done with the IDSK. Again, I can't fully talk to this, but putting that in there. So if you want more information on that, definitely let us know and we can get that to you. Oh, looks like there was one question that popped up.
Is the temp dashboard via Violet or another tool?
Yeah, it's actually, in this case, it's via another tool. And can't immediately tell which tool it is, but there's also you can do it via Violet, and there's just kind of depends on which way you want to visualize it.
But dashboard, and you said it could be like via Violet, is that like any program office can make it their own, like, but however their dashboard is, or will it be like a standardized, like, this is the ton dashboard?
Oh. Yeah. I think the answer, is kind of more dependent on what the policy defines. So technically you could make your own. Right? If you want to have it individualized for a program or like a project group, I'm sure you can do that. The expectation seems to be that it's going to be something that has some level of standardization, maybe more with like the content, but ultimately it's going to come down to what the decision makers say they want for that dashboard. And it's probably going to maybe even dictate which tool you use. So that's why we're trying to take this approach where it's independent of the tool that we eventually choose. Like, one of the tools I used in the past was Confluence. So, maybe that's just the tool that your part of the government ends up going with. And we can visualize the data even within like a Jupyter notebook as well. All right. Any questions? Other questions? No? Jeremy, is there anything I missed up to this point?
No, I don't think so.
Okay. All right. So I want to remind everyone, I'm not going to step through this, but this is the vision again. Ultimately, we want to get to this piece, but for right now, what we're actually focused on is more of this piece and establishing like the dynamic decisions. The way we're viewing T&E is it's ultimately about confidence that the system is going to lead to mission success. And so that's why you see things like, as you're actually reading this, it says, confidence levels, and ultimately leading up to the, final product or fielded product. And, there are some tests you're going to do in development, some tests you're going to do during like operation. And ultimately there's like one system level or even mission level confidence level that you're going to have. Okay. Yeah. All right. This is where I'm going to explain a little bit more detail, like what we're trying to do. And so imagine you have a developmental system. This is maybe not quite to its final form yet. And let's just say you do 3 developmental tests. All right, now we talked about earlier where you might have different terrain or different environments. So in this case, you have maybe a cold mountainous region, maybe you have an urban region, and maybe you have a hot, dry desert climate. Now, let's just say that you have high confidence in the cold, humid mountain climate and high confidence based on your test in your urban environment. But when you start getting your desert climate, that's when you see you have low confidence in your test results. Now, like what should you test when you get to your operational tests? Now, based on policy, what it says is it's entirely independent. Right? So you can basically retest all of these if that's what the operational test authority decides to do. But, in this case, what we're saying is that essentially we're going to test. And because we had lower confidence in the desert and higher confidence in the urban and rural, mountainous, cold environment, that we're probably not going to test on the actual fielded system, the other two. So, I mean, essentially what this is saying is it's an aggregation of both the data and our confidence in the system. Now, in reality, these are going to be really complex testing. It doesn't necessarily have to do this. It's not going to be this simple. There's going to be a highly complex network. And what we're trying to get is to more of a dynamic set. You can imagine even within, if this wasn't labeled as like developmental test, it was maybe just all operational tests, but it was a series of tests. What this really means is that you should be able to change the trajectory of the tests based on the confidence level that you achieve within a specific test. I mean, if you're just testing and this is the final system and you've got a set of operational tests, you should be using that knowledge set to inform what you're doing in the future. And so that's some of what the digital engineering enables us to do. It is partially because we have the means to aggregate that data and to, I should say, not necessarily automate, but at least harmonize the data across different tools and to make it more efficient of the, say, transmission of data across different platforms. We're able to ultimately get to this like system confidence level and enabled us to be able to change our plans as well. Any questions on this? Is everyone, I should have asked earlier, is who's not familiar with Bayesian networks? Okay. Should have asked it earlier. So essentially the way this works is that you have your, typically this will be like a percentage right here, and it'll all add up to 100. And so that gives you like a confidence level, but you can also see there would be like maybe a lower percentage down here. So that would feed up to like this test as well, and ultimately feed down to a, which path do you go? You're probably going to have a really low confidence, like 3% and 97 if you go this route. And so what you want to do is typically it's kind of weird the way it looks right here, because typically like there's this massive and you have a lot of like different data points over here. And ultimately you have to do some math to really flip this to where it looks like this. But you kind of read it from a time perspective of, if we go this route, There's like there'd basically be a test, no test, and then it'd feed up into this end result where you'd have this aggregation of, desert test, no test. Ultimately, what your confidence level is in the final system. And so what we do with Bayesian networks is essentially, again, use the tools to basically flip this to give us this top level confidence in our system. Yes.
Does this take into account the fact, like, at least how you have it pictured here? The developmental system is completely different than the final system. So is that taken into account when you determine where to operationally test? Like let's say the clearance level is lower and it's no longer wheels, it's treads. That may affect you in the mountains if you have big rocks. And now you can't clear those rocks. Does this method have a way of taking that into account? What's changed?
Yeah, so that actually, so yes, there's kind of a yes but here. So it's yes. So essentially, some of the confidence that you'd want to include in here is an understanding of the similarity between your developmental, say a prototype versus your actual fielded system. And so right now we're getting there. So some of that gets to more of the phase 3 of understanding you can call it fidelity, maybe, or I like to call it more along the lines of equivalence. So equivalence both of the systems as well as the context of what they're tested in. So that's the direction that we're going. So that is a great question. But that's why we're at phase 2 right now, is because we have to mature a little bit of the methods and even do more of the testing so we can prove in. Like we have the set of math that we want to do to underpin it. And I actually do have a quick demo on that at the end that I'm going to show. Double checking time. Yeah, I should have time.
One more
But
question
yes.
from Nicholas Jones. One thing that may be difficult here is that DT and OT are often focused on different responses. Does this Bayesian network approach require quote unquote operationally focused DT or building a prior for OT?
Yeah, I mean, it can. I mean, there are different, like what we're trying to do is essentially like create different scenarios. Why we're really using the Lego robots is because like we can create the set of data and then change the story arc to really reflect a more realistic scenario. So like an example you could even go from this is, let's just say this is the existing legacy system. And we find a flaw in it, but we still know that some of the testing we do is relevant to a future system that we're in development. So you can look at it from a transition of legacy system to new system as well. Jeremy, is there anything you want to add?
No, that's perfect.
Can I address your question? All right, so here's the architecture for how we're actually creating the model-based temp. So you can see here where, at the top, we have different models. You've got your mission models, your system models. So essentially this would be what would live in your MBSE tool. In this case, it actually says this is MOV2. So I'll talk about that in a little bit. I think I'll do that in a couple of slides, but so I won't talk about that yet. Then you have your modeling and simulation, which in this case would be Python. You have your user interface for your temp, which in this case, the input would be from your organizations and defining a lot of your test strategy. So test strategy in this case, I think we're using that more from the perspective of defining your plan for your temp, but also getting to the point where we really want it to be dynamic. And so that's when we have a tool that allows us to define the Bayesian networks, where we can, at least the initial test strategy can define what maybe those pathways would be, and through the different tests. And then as we get results, those would be updated, and we'd have new levels of confidence that we'd have associated with the test and to be able to change this. And then last, there's that IDSK, which really defines the content that would be going into the decisions. And Violet We've got a demo video on this. That's where we're using our data harmonization. That's our data harmonization tool. So we have the ontologies, like the temp ontology that really feeds into this. And you can see here the NB temp. So we have the ontology stack that UA is using for different like systems engineering in combination with the NB temp ontology, which is based on the TUD 5000.90, well, .89. I think they may have updated it to 97 as well. And then ultimately it gets visualized within dashboard. Yeah, how this looks like, getting some different views. So again, there's the ontology stack that you have here in the middle. And, then you have the data that's also visualized. It's labeled as dtemp here. It's the same thing, really, as mbtemp. It's just like we kind of use it interchangeably just for awareness. Then you have your data library that's really program specific. Then you have the ability to actually start conducting some of the reasoning behind this and ultimately feeding that up into your dashboard, which would be based on specific queries. In this case, they're using Sparkle, which is like the SQL database query language. Yeah. Here's another view. I showed this one earlier. Ah, yes. Okay. Yeah. Okay. So, yeah, this again, I want to give Arizona credit. So this is kind of the ecosystem that they've built. We have something similar at Virginia Tech as well, but they've made like a really pretty image, so they get the credit here. And so I've got a bunch of different tools here in the middle. You can see they've got Cameo, and let's see, SysML v2 and Genesis over here, which are more of your MBSE tools. And I actually don't know what Quick Kiwi does. That's one I'm not really familiar with, but there's Jira over here in Jama, which they can use for things like schedule tracking and and assigning tasks. And for SysML v2, we're using two different tools. One, we're using the Jupyter notebook version of SysML v2. So if you're familiar with SysML v2, there's the Git repository, and you can start using a Jupyter notebook for it. There's also an Eclipse version. I kind of prefer the Jupyter notebook version because it allows us to do things like integrate with PS Studio and all. And there's another company called Syson that has the SysML v2 tool as well. Oh, I mean, that's not the company, sorry. That's the tool. Ansys makes one called the System Architecture Modeler, I think, SAM. So that's another SysML v2 tool that you can use. So you can see that in this case, they're using GitLab to have a repository for some of the code and more do the Git repository and some of the branching and merging, I believe. But ultimately, the data is harmonized using this tool that we call the Violet. It's made by Violet Labs. We're latching onto this as well at Virginia Tech, and I'm using it in some of my class, and it seems to be a pretty good tool. It's based on ontology, so a lot of those UA ontologies and the model-based temp ontology, it feeds into this. Excuse me. And what that enables us to do is to have some of the common elements and to merge a lot of the, so I should say merge, harmonize the data across these different tools, which ultimately enables us to publish this. Now there's another one down here called the ontology modeling language. Should be actually Rosetta. That's a tool that's created by, was it the Jet Propulsion Laboratory, I believe, and the Open Caesar initiative as well. And so this is a way of treating the data, another ways of making sure it's ontologically consistent across the different tools. So what's published, I believe in the case of where we're at in the maturity of these tools and the methods is that it's published, some of it can be published as part of Violet and some of it actually can be published as part of OML. There are other ontology modeling tools that you can go out there. Protege is one of them. Don't believe it's authorized to be used on government equipment, and it's more of a visual ontology modeling language, but OML and Rosetta are textual based. And so that enables you to do a little bit more advanced data analytics than you could otherwise do with the Protege version of an ontology model. Okay. Double check time. 20 minutes. All right. That's good. Okay, so kind of making a simplified view so you don't have to stare at some of the complex things that were shown over the last few slides. So essentially, what we have within this Operation Safe Passage and Operation Safe Lego, you can just think of it as this small subset where you have a set of more MBSE tools, King Systems Modeler, Python-based System LB2. We have some more CAD and multi-physics type software that might be lived here in the middle. And then we have this OML Rosetta, and then we have Violet, which helps us to harmonize the data. And then over here, you can see we have some physical pieces of the robots, where there are different configurations, maybe of the EV3 Mindstorm. And then here's the Spike robot. That's the newer version. It's much more slick and seems to actually have a lot of improvements. And then from an environment perspective, we've got the different terrain, different places, the desert of Arizona, and then the mountains of southwestern Virginia and Virginia Tech. Okay, I do want to give again credit. So I keep expanding like our team. These are all of our students, plus me on here that have been working on this at Virginia Tech. So they've been developing a lot of these models. I mean, gosh, I'm not even going to be able to show you like all the models. If we had moved this by like a month, I'd be able to show you a lot more. We're kind of the point where we're collecting a lot of the data and we're putting it into this format that I've kind of showed you now. So I'm like right there. Oh man, maybe even like 2 weeks. But these students have done a lot of really awesome work this year. They've developed models that are in Cameo to represent the Spike and EV3 models. The full so what we're doing is developing a reference model for the kits. So essentially the way that should work is that if you want to create a different configuration, you should just take that parts kit and say, I need these subset of the 1,000 parts, maybe 100 parts to really form a new system. And so we have that parts kit that's being made. I think it's pretty close to being done, but also the specific configurations that we've used for the EV3 and the Spec Robots kit. We have some mechanical models that we've been working on. We have some electrical models that we've been working on. We have some software models that we've been working on. And oh, by the way, we have that physical test that we've been working on. Excuse me, sorry. Okay, so here's a test procedure that we've worked on. This is more for how we actually may conduct some of the tests. We've really focused the testing on two pieces so far. One for looking at the terrain and the battery life and understanding the interplay between that terrain, the environmental conditions, heat, cold, and how long the system can actually operate. We did do some analysis to look at adding in what the tire dimensions may change in the outcomes as well. And you could think of this is an earlier one that we did with the tires, where if you change the dimensions of the tires, let's just say you double the tires, you can go over rocky terrain, right? But it's going to decrease the mission life that it can take, right? But if you do smaller tires, it can increase, but it can't go over this rocky terrain, right? So that's some of what I think your question was getting at earlier. So are we incorporating that? Yes, there's still a future state though. And so we can incorporate that and that knowledge set into how we might change in the future tests, or how we might use some old information to inform like a new test strategy. And we've also looked at, I think they're actually doing it today. I just talked to one of my students last night, and I think they're wrapping up some of the detection of the sticky notes today. And so they'll probably have some of the data. So unfortunately, I can't show it to you. But so earlier, I think since we have a new person, we're doing is using a surrogate for detection of landmines for sticky notes in Lego robots. And it turns out it's kind of fascinating how it gets like false positives or misinterprets the color. And you can imagine how we can change this and mold this into something that is fairly similar to what you see, but obviously you're not exploding things or causing loss of hardware or limbs or any et cetera. But we've gone through this and we've conducted several tests for the batteries. So I've got this on the next slide. You can see we have the Spike EV3 robots. This is just an example of some of the tests that we've done. So in this case, we have so I mean, essentially, this is a really simplistic view of some of the things that we've done, but we've basically gone through and set these to go like back and forth. So we can look at the temperature, continue these measurements that you see on the right side of the temperature of the battery and different like environmental conditions. What's the environment inside? What's the environment outside? We had hoped to actually do this test on one of the really cold days in Blacksburg, Virginia, but we didn't quite make it. So some of what we had to do is inside. This summer, I'm imagining that we'll do it in like the hottest part of the summer in Arizona, and maybe even some of the more humid, hot parts of the summer in Virginia as well. Check my time. Okay. So here's just an example of what Rosetta would be. I've got to click through this. Is a really long video. So I've got some examples of ontology in here. Oh, it shows the tool. Where we go? Okay. So in this case, that's Joe Gregory. He was kind enough to give this lecture to my digital engineering class at Virginia Tech on ontology and using Rosetta. So what you can see over here is the Rosetta interface. This is where the ontology would sit for the model-based temp. And because it's code-based, or text-based, I should say, allows you to do some data analytics that you wouldn't be able to do maybe on Protege, which is more graphical interface. But this is an example of where you might, or of where we are defining that ontology that allows us to have that harmonization of the data. All right, I've got this again, another video. Double checking time. Okay. So this is also, so Lucy, I believe her name's pronounced Hogue. She's the CEO of Violet Labs. And so here's a look at some of it. I've also got, I think I can actually pull up some, I'm gonna pause it there because I can actually show. So there's Lucy. She's been a partner for both us at Virginia Tech and at the U of A. And so we're using this tool. You can see in this image where it's got different connections to different software. You can test some of the parameters. Let me see. This is where I actually need to exit. I don't want to do anything too live because I don't want to break it. But I do have this. So this is a look at one of the instances of Violet that we have. And you can see here we have things like the different mass parameters, total mass, moment of inertia, torque. And so you can start defining this from an ontological perspective in Violet. And in this case, it's looking at a rover, I believe. It's not the one that we're quite using yet for this project, but it would look pretty similar. So let's see. Let me go in. Yeah, so you can see here what they have are the JAMA that's connected to this. You can see where we have the System LV2 Jupyter Notebook and data plugged in. And I guess there's a lot of System LV2. Wanted to pull up. I really wanted to pull up some of the capability that Violet has. Doesn't look like I'm quite going to be able to do that. But essentially what you do is you define based on the ontology, you make those connections, you set up a project, and you're able to, then connect the data across different tools. And that would allow you to, again, make sure you have that consistency and the harmonization of the data across the tools. So if you want more information on Violet, I can definitely talk a little bit to that. And I would say also point to Brant when you go see his poster tonight. He can talk more to Violet as well. And we're happy to share more information on this. So ultimately, again, that would look like a dashboard. I showed this earlier, but what you want to see in a dashboard are things like what was shown and what I showed you of Violet, where you have your schedule elements, and that allows you to see duration. It allows you to see that you have test events, but maybe they haven't actually been scheduled yet. In this case, you have 0 upcoming because you haven't scheduled those 2. Or maybe you've actually completed 2 and they're considered, or at least completed if not successful. But by the way, you have like some way of visualizing what the outcomes of the different tests are. Here you see that the electrical test has a potential schedule conflict with another test, so you can do that schedule conflict. But some of these are more scheduling centric. But ultimately, you want to be able to see like the confidence level, which isn't quite shown here. And to be able to do this in like a dynamic nature that would really feed back across your different ecosystem. And here's kind of an example. I think I mentioned this earlier. If you can look at it from different perspectives. Like one of the ways we've done this is we've actually tested the EV3 Lego legacy system. You could say in the desert, we tested it in the mountain conditions, multiple tests. Like I don't know, how many runs have we done, Brant? Do you know?
3 tests, but each test ran about 9 hours.
Okay, yeah. So essentially we're testing multiple times. And what you could think of this from an alternate perspective is how do we form a new system, which in this case it's the Spike robot. And so what's what's shown here is more like, so and a really simplified example could be, well, we know the runtime temperature in the older system is probably going to be worse off than our newer system. So to what extent we need to do some of this testing, maybe we can reduce the amount of testing that we need on the new system. Okay. Yes, good timing. All right. Kind of going back to some of the vision for how we're going to do this and focusing more on some of the future piece of this, which is really getting to that underpinning of math to the data and models across a lot of the ecosystem. So this hasn't really been done as part of this project, but it's something that we've been working on a little bit on other projects. But it's pretty interesting. So essentially what we've done is you can see some of the code in here. So what we've done here is this is actually also working with a lot of the generative AI. So in this case, we use Gemini to really provide this input that says like, hey, I want to develop an autonomous vehicle. and it might give some initial parameters within a textual basis that you ultimately feed it to this generative AI. A lot of it also has mathematically based ontological considerations. That's something that's a work in progress right now, but this does have math based. And what we've been able to do is to work with this generative AI agent and to say, hey, if we give you this description, can we produce an end-to-end and fully mathematically traceable context that has the requirements, the system design, the ability to differentiate between acceptable and unacceptable system designs, and your verification. So what are your verification requirements? I'm not quite getting into plans yet, but also what are the acceptability of different verification models that you can actually use? And oh, by the way, it's all mathematically traceable. Oh. But we've been able to do that. So you can see this is just a really simple user interface where we able to produce like what's the system design, what's some of the requirements. And you can see where it starts defining even like the degree of fidelity, meaning the degree of equivalence between the verification context and the system requirements context. And what's the degree of fidelity between the verification models as well as the system designs. And so you can see where we started to do this and even in the end, this traceability. Oh, that's good enough. In the end, it starts being able to have this like fully mathematically traceable. So it's something that's a work in progress. And again, that's something that's more of a future state than it is like a now state. I've got one more slide. And so that's, what are we doing? What have we done yesterday? Well, we're like the test and evaluation. It's not just about the systems or even the system of systems. It ultimately should lead back into mission success and even campaigns, capabilities. It's partially about visualizing some of the data and defining what some of that data would be, like the IDSK, integrated decision support key. It's like, what form should that take? Well, model-based temp. What should it support? Decisions and communication. That's where you come into program reviews. Ultimately, like the approach that we're taking is that we need a test bed, something that we can control the complexity of and have controlled growth even. So that's why we've latched onto things like the Lego robots, because we can add further complexity to this. It's something that most people can understand. It's something that if we break, doesn't cause a catastrophic failure. If we break one part of this, it's, pennies versus potentially like millions of dollars. And so we can incorporate things like if maybe we even want to incorporate some more expensive things, like do we want to structurally test like the computer unit? That would be maybe something similar. I've talked to one of my students about doing a drop test on one of the computers and why we might not want to do that versus why we might want to do that more in a digital side of digital modeling. Well, it's expensive, right? And it's not just expensive, but there's limited supply. And if we break it, do we actually need to use it in the future maybe? So it's more of a, how do we actually take these models and use them to inform a lot of the decision? And what we should be doing is, or the idea is at least, that we can reduce a lot of the expensive and from a time and resource perspective, physical tests. So what we're doing again is like just growing this, and we've got a few things that we're continuing to work on. And a lot of those are hopefully with the support of Jeremy.
Yes. We do have, yes, absolutely. We do have a question. So I think it refers to the previous slide. Was the system design just showing AI generated from the inputs that?
Yes, it was.
Okay, got it.
Yeah, so just based on the inputs, it was able to define like a system within the mathematical framework that we got. And I can elaborate on that. I was kind of giving you an idea of some of the futuristic, well, I shouldn't say futuristic, but the maybe near future that we're working on. That's maybe not quite ready to insert into practice yet, but it's still pretty darn cool. It is 11:59. So I have 1 minute for questions. If not, I'm happy to get applause, hopefully, and talk to you offline.
Any questions?
One question.
But I've found in practice, the digital engineering is a lot easier to incorporate on a nascent product and we're very, very, very early in the systems requirement phase versus retrofitting, you know, something that's already existing with its own architecture. So I was hoping like, you know, do you have any like low recommendations on like the low burden to implementation methods that could be incorporated in an existing architecture that might, you know, be worth incorporating that aren't like this huge ecosystem that would take a number of systems engineers to like roll out.
Okay, I have the things that I'm working on that I can probably share. And so this is kind of a more of a I think there are tools becoming available, but some of the generative AI capabilities are enabling you to actually automate the creation of these models based on existing data. So like one of the things I've done in my research is take like two-dimensional drawings and convert those into SysML v2 models. And it does a pretty good job of doing things like that. And if you have a language model available, it's that's within your network, you can, I'd say, tailor it to your specific needs so that it creates the right set of models. That would be where I would go. You know, there are some other things. One of the earlier questions was when is the model good enough? I think that was kind of where the question went, which I think is also what you're asking, which, you know, I'd hope that maybe there's a simplified look at some of the architecture. Maybe you can just model at the subsystem level rather than going down into the components. And ultimately, some of what you should be doing is thinking of it in terms of, is my model useful? And what level of detail do I actually need to frame the actual data that exists to really ultimately do what we're trying to do, which is more effective and more efficient decisions and communication. And so that's why I'd say maybe start at the subsystem level and start feeding into that. Maybe you need just like something even higher than that. But yeah, I can think of definitely different things, but I'd probably continue to pontificate on it. So happy to talk to you further. But thank you for your question. Anything else?
All right, cool. Thank you all.